Virtual reality, or VR, is a computer generated simulation that allows users to interact with a three dimensional environment in a seemingly real or physical way. Unlike traditional user interfaces, VR places the user inside the experience. Instead of viewing a screen, users are immersed and able to interact with virtual environments. To understand VR from an engineering perspective, we must look at the hardware systems that make immersion possible. User movements are captured through input tracking devices such as head, eye, or motion sensors. The system processes this data and updates the virtual environment. Then, output/stimulation like visual, audio, or haptic feedback is delivered back to the user. This continuous loop creates an immersive VR experience in real time. At the core of any VR system is the head mounted display, or HMD. The HMD consists of high resolution displays placed directly in front of the user's eyes. These displays render slightly different images for each eye, creating a stereoscopic 3D effect. The lenses inside the headset help adjust focal distance and field of view, enhancing immersion. Modern VR headsets typically provide a field of view between 90 to 120 degrees, which significantly increases realism. Another essential component is the tracking system. VR relies heavily on accurate tracking to detect head and body movements. There are two main types of tracking: outside in tracking and inside out tracking. Outside in tracking uses external sensors or cameras placed in the environment to track the headset and controllers. Inside out tracking, on the other hand, uses cameras mounted on the headset itself to track the surroundings. Inside out systems are more portable and commonly used in standalone VR devices. Motion tracking is achieved using sensors such as gyroscopes, accelerometers, and magnetometers. These sensors measure orientation, acceleration, and rotational movement in real time. The data is processed to update the virtual environment instantly, ensuring low latency. Maintaining low latency, ideally below 20 milliseconds, is critical to prevent motion sickness and ensure a smooth experience. Input devices are another key part of VR hardware systems. These include handheld controllers, including data gloves, haptic devices, and motion trackers. Controllers typically include buttons, triggers, and touch-sensitive surfaces, allowing users to interact naturally with virtual objects. Advanced systems incorporate haptic feedback, which provides tactile sensations to simulate touch and physical interaction. Audio systems also play a crucial role in immersion. Spatial or 3D audio creates the perception of sound coming from specific directions and distances. This is achieved using binaural audio processing techniques. Proper synchronization between visual and audio components enhances realism significantly. The processing unit is the backbone of the VR system. VR applications require high-performance GPUs and CPUs to render complex 3D environments at high frame rates, usually 90 frames per second or higher. A high refresh rate is necessary to maintain immersion and reduce motion sickness. Some systems are PC-based, while others are standalone devices with integrated processors. Another important aspect is the display resolution and refresh rate. Higher resolution reduces the screen door effect, where users can see gaps between pixels. Higher refresh rates ensure smoother motion rendering. Finally, VR hardware systems must address ergonomics and user comfort. Weight distribution, ventilation, adjustable straps, and interpupillary distance adjustment are essential design considerations. Poor ergonomics can reduce usability and limit session duration. In summary, virtual reality is made possible by the integration of multiple hardware components, including head-mounted displays, tracking systems, motion sensors, input devices, audio systems, and high-performance processors. The effectiveness of a VR system depends on how well these components work together to deliver low latency, high resolution, accurate tracking, and immersive interaction. Understanding VR hardware systems is essential for engineers working in fields such as computer graphics, embedded systems, robotics, and human computer interaction. As technology advances, VR hardware continues to evolve toward lighter, more powerful, and more immersive systems.